Hello, we are team 563-4, and today we'll be sharing with you our final presentation on our 3D printed Sharpie holder. We will begin with an introduction to the background and purpose of this project. This report will include a description of our entire process undertaken at Project 5. We will cover our use of SolidWorks, Cura, and RobotStudio software, as well as the Ultimaker 3 3D printer and the ABB IRB 140 robot to accomplish our purpose of designing and creating a pen holder to draw a picture of the Ann Arbor skyline. For our agenda today, we will begin with a video of our final drawing, which I will introduce. From there, Sam will elaborate on the CAD design process of our pen holder. Charles will talk about our setbacks as well as our future improvements to make, followed by Ben providing an outline of our past and future work, introducing our simulated toolpath, and discussing the societal impacts of robotic painting and presenting a plan for our proposed impact study. Finally, Liam will end our presentation with a conclusion encompassing everything we have talked about today. Before starting the video, I'd like to introduce the important elements shown in the video that will all be elaborated on later in the presentation. First is the toolpath used to create the drawing of the Ann Arbor skyline. Additionally, you can see the specific design elements of the pen holder that will be pointed out later, including the linear metal spring, hinge connector, Sharpie holder, and the mounting plate used to connect to the robot itself. Lastly, there is a jump in the latter half of the video. This is simply to cut out a lengthy pause that occurred in the middle of the drawing process. Next up, Sam will be discussing our CAD design.
All right, so to begin our CAD design, I will start actually at the end. This is our final assembly and our final design. So the key elements pointed out here are the hinged right angle joint forming the main body of our piece pictured in the upper right hand of the image, the single MC set screw and nut, which is inset in the plastic, seen in the bottom and the top images, the linear metal spring, and then the friction fit holder for the Sharpie pen. So our design process began with a piece of paper where we sketched out the requirements for what our design was going to be and what we needed to have. Our idea was to provide compliance for compression should we crash the robot. We wanted about 1 centimeter of play and 15 degrees of angular movement. To do that, we decided to go with the hinged right triangle idea, which is seen in our first CAD draft in the bottom left. We decided to go with a linear 3D printed spring to prevent any breakage and give a nice compliant mechanism. The holder for the Sharpie comprised of a circular tube with a hole for an M3 set screw to hold the Sharpie in place. After completing our first CAD design, we went through some first revisions without producing it, thinking of what are some things that could be improved upon with this design. One element that we thought could be improved was that even though the tool holder fit on the flange of the robot, it wasn't secure rotationally. To solve that, we added a second M3 set screw attaching to the shaft, seen in the bottom right image. We also decided to switch from a linear spring to a serpentine or flat spring. This was due to the unaffixed end of the linear spring that would allow it to rotate. The tolerancing design for this would be first printed with 0.2 millimeters, giving us hopefully minimal friction and free moving parts with good assembly time. So a cutout on the left here is the serpentine spring with a little more detailed explanation. In our process going through with this, there were a couple of key considerations. The main thing we were trying to solve was the rotation of the linear spring. To achieve this, we put a small tab in the bottom that would fit into the channel in the moving arm of the Sharpie holder. Those are pictured in the bottom left corner. The round contact points designed with a radius of 2 millimeters still fit within the tolerancing of the printer, would hopefully give a smooth motion when being used. Our first print is seen on the right-hand side, and there were several issues. First of them being that the tolerances we designed were too tight. Our parts had almost the same dimension. There was significant friction when they were assembled, and it took a lot of post-processing to get it to work. The spring was too strong, so even though it was designed to be a compliant mechanism, due to the resolution and size that it was printed at, it ended up requiring significant force to bend, and the flange of the rod actually wound up bending when it was fitted on there. So we decided that we would change that up. And then lastly, the print resolution on our M3 set screw holes wound up, instead of filling with support material, they wound up being filled solid. So we weren't able to put any M3 set screws in there, and our parts were not fixed. So our secondary revisions that we made were to remove the set screw on the Sharpie holder. Now that was because it was designed with the same 12.4 millimeter diameter that the lab Sharpie has, and it was actually able to be friction fit inside. So that was an unnecessary element. We also decided to replace the circular hole and extrusion to hold the M3 set screw with an inset nut. This is pictured in the bottom right. The hexagonal channel there is to fit a steel nut in that allows for the printer to print holes that are within its tolerances and us to still have the part be secured on the flange. We switched out the serpentine spring for a linear metal spring, similar dimensions, and the force it required to compress it was significantly less, so it gave us an ideal mechanism. We also adjusted the tolerances in the Cura slicing and in the printing, and also in the CAD to hopefully give us minimal printing time. Our total printing time from the first print to the second print reduced from being 1 hour and 20 minutes to around 1 hour and 15 minutes. With our improved tolerancing, our assembly went from roughly 30 minutes to roughly 15 minutes. So the second design was a significant improvement. Pictured on the right side here is the final edition of our design with minimal joint friction, easy and smooth compression, and it was very secure on the flange. Next up will be Charles with some of our issues.
Yes, a first issue that we had while doing this project was that our Ultimaker 3 printing resolution was not suitable for what we were trying to print. So our 3D printed parts had excessive frictions, as Sam mentioned, and the mounting holes were sealed. To fix that, we just went through multiple revisions, editing dimensions, and using different springs. Another issue was that when we went to lab to mount the pen holder to the robot and the flange, it required significant repositioning from how it was when we initially found it in lab. So attaching the set screws also required an additional set of hex keys. And the final issue was that our art did not fit the width of a separate surface other than the whiteboard in lab. So just instead of using that separate surface, we simulated in RobotStudio. Next is possible improvements to this project. The first would be to edit the toolpath to lift the pen at the surface at corners. So this would eliminate the possibility of a ruined drawing from changing directions. This will make it less likely that when the robot changes directions, that any of the pen's ink is not adequately on the surface. A second improvement would be making a less linear art design, which allows for more complex RobotStudio code usage. And a final improvement would be to make a different RobotStudio environment that was more similar to the additional surface from lab, which would allow us to test our pen holder in multiple circumstances. And next is Ben with the simulated toolpath.
So here's our RobotStudio simulated toolpath, and you can see it's very similar to the actual video you saw earlier in the presentation of the recorded toolpath in the lab. And some of the issues with our initial design of this toolpath were initially we had lots of little details like windows in the buildings that we decided to remove later because we realized that the thickness of the Sharpie line would be such that you couldn't really tell those details and they would kind of cloud up the drawing a little bit. So removing those made for a more clean, nicer look for our drawing. Here's our chart for the project deliverables. As you can see, this is the last week of the semester, and this wraps up all of our projects, and then we've kept on time and on schedule with these throughout the semester. As far as the societal impact for robotic painting goes, we believe that robotic painting would result in a net devaluing of art, and this is from both an economic and a cultural standpoint. First of all, if robotic painting were to be introduced, the supply of art would increase, and basic economics tells us that as supply increases and demand remains the same, that value decreases. So just from that standpoint, the value of art would be decreased. Secondly, there's something special about art that celebrates human uniqueness and originality and creativity, and this would be lost with robotic painting. Robotic painting is in some sense similar to just printing. As you can see, the picture on the left here is a painting of Grand Teton out in Wyoming, and on the right is a picture of the same place. While the picture on the right is definitely a more accurate representation of what the subject actually looks like, the picture on the left, the painting, is much more valuable because it's done by a human. We don't value art because it's accurate. We value art because it's special and it's created by a human. We recognize that although we could have a more accurate representation, we choose a more unique and creative one. And so robotic painting would result in a devaluing of art in general. To test this theory and to see if that's actually the case with real customers, we proposed a study with 2 focus groups where we'll try to answer the question, how will the value of art change if robotic painting is introduced? We'll have 2 different focus groups. The first will be consumers of art, and we'll ask them 2 questions. The first is, how much would your opinion of art change if robotic painting were introduced? We'll also ask them, how likely are you to buy robot painted art? These questions will help us gauge the consumers and the people who will be buying art, gauge their interest in robotic painted art to see if the value will increase and decrease. And secondly, we'll ask those who create art whether or not they'd use this technique. We'll ask them how their robotic painting processes would change the creative process, and how would their opinion of robotic painting art change if other artists would start to use those robots. We want to see that maybe there's a little bit of a curve for creators, that if many of them start to use this new method, then the whole industry would start to use it. And also with these, since they're in a focus group, we can ask follow-up questions, and we can quantitatively and qualitatively gauge interest in robotic painted art. And then finally, we'll record data based on various demographics to see if there are any trends in the answers with those demographics. And finally, Liam will conclude our presentation.
I will give a brief overview of everything we've talked about in this presentation. So first, Nick led us off with basically the goal and purpose of this final project, which was to use the ABB robot to draw the skyline of Ann Arbor using a Sharpie that the robot held using our designed and printed pen holder. We then went on to a video of this happening in our final lab. And as you saw, it was very successful. The robot successfully and accurately drew the skyline of Ann Arbor as we predicted. Then Sam went on to discuss the final assembly of the pen holder. Just a brief overview of the major features. It had a hinged joint, it had friction, and a metal spring for compression. Sam then went into detail our entire CAD design process and the various steps we took. Initially, we wrote down on paper several features that were important to us, such as compression to allow for flexibility if there was ever any extra pressure placed by the robot so that our pen holder would not break. We also wanted the pen to be held at an angle and some other things, as Sam mentioned earlier. So some first revisions we originally had a linear or spiral spring, but we switched that to a serpentine spring because we thought the linear spring would not remain constant on the flange shaft. And from the first print, we discovered that the serpentine spring is not necessarily the best plan because it was very rigid and would not allow for the desired compression we had. A second revision we made was to instead use a metal spring, and we also used wider tolerances because this was an issue with our initial print where the tolerances were too tight and then the assembly of the pen holder was too difficult. Then Charles talked about the issues we encountered during this project. This included that the printing resolution was not as good as expected, as Sam also talked about. And when we were given the second surface in the final lab to recreate our drawing on, that was not possible because the Ann Arbor skyline was too big to fit on the second surface. And also some potential improvements that Charles talked about were to lift the pen up at the corners so that the drawing would be cleaner and that ink would not necessarily be drawn if the robot was moving from one spot to another if we did not want it to. And then also he talked about having less linear art, which would be more complex and use more of the features that the ABB robot could handle. And then also, as mentioned earlier, we could write on different surfaces and simulate different environments. Then Ben talked about the simulated toolpath using RobotStudio, and it was very similar to the final results. He also talked about the Gantt chart. As you saw, the only thing we have left after this presentation is the final report due Friday. And that he talked about the social science impact, and that having robotic painting would devalue art, because less people would, it's less ideal to have robotic painting, because one of the main values of art is human creativity. And this would basically go away if robots started doing everything. And then Ben proposed the study that we would have two focus groups, one of consumers and one of artists. And these would basically just examine how their opinions of art would change with the use of robots, and whether they would be more likely or less likely to purchase or produce art as a result. This concludes our presentation. Thank you for listening.